Okay, now let's see this question. This question came in GATE 2016 for 1 mark. The question is, consider the following directed graph. So this directed graph is given and the question is the number of different topological orderings of the vertices of the graph is what? So for this directed graph, we have to find that how many different topological orderings can be there. So what happens in a topological ordering is that the vertices in the topological ordering should occur in a way such that if there is an edge from a particular vertex to another vertex, then the first vertex should lie before the next vertex. Okay, so I mean to say is that if there is an edge from B to C, then in that particular topological ordering, B should lie before C. Similarly, C, there is an edge from A to B. So in any topological ordering of this graph, we must have A before B. Okay, so something like if A is here, then B must lie after A because there is an edge from A to B. Okay, similarly C must lie after B because there is an edge from B to C. Similarly, there has to be an ordering among D and E such that D should come before E. So something like D must come before E. But note that there can be different topological orderings for the same graph because see, B should come before C, that is okay. D should come before E, that is also okay. But there is no relation between C and D in this directed graph, right? So we might have a situation something like this also. So rather than having D and E here, we can have D here and E here also, right? Because this also follows the condition that D should come before E and B should come before C, something like that. But we don't have to have any condition regarding the placement of D versus C. Okay, so this is the situation which we are talking about. Okay, so let's understand that how many different topological orderings can be there for this graph. Okay, see, A must come before everyone else. Why? Because there is no other edge which points to A, which means that if A is the first one, then it is okay. Similarly, F can be the last one because after F there cannot be any other edge because there is no edge something like F2 something. Okay, so if there is some edge that is sinking to F, so F can be the last one, but there is no node which is having an edge such that F points to that node. So there cannot be any other node after F. So we have come at a situation where F will be the last one and A will be the first one. Now let's consider it in terms of slots. So we can understand it something like there are 6 slots, okay, and we have to fill in the different vertices in these slots such that the properties of a topological ordering is satisfied with respect to this directed graph. So as we have already mentioned, A will be the first one, F will be the last one. Now we have to consider how many ways the rest of the nodes like B, C, D, E, these can be put here. Okay, so let's start with a simple situation. Let's say we put B here, and so let's firstly choose any 2 nodes from these 4 slots. So let's see that we are choosing these 2 slots. Now what happens that once we choose 2 slots from these 4 slots, and if we put B and C here, then there is only one way in which B and C can be put within these 2 nodes, within these 2 slots, because there is an edge from B to C, so B must lie before C. So only one way, B here and C here, can be put. Now rest 2 slots are there and 2 nodes are there, and there is only one way to fill, so D must be here, E must be here. But what if we choose a different way, that we choose 2 different slots? So we can have something like this also. So let's remove all these and let's consider about a different situation. Let's say we pick 2 slots, something like this and this. Then what happens? Firstly, let's say we are going to put B and C. So there is only one way. B here and C here. That is the only way we can put. After that, whatever the two slots are remaining, there's only one way, D here and E here, because D should come before E. So we can quickly understand that the problem boils down to that in how many ways we can choose two slots from these four slots, and that is our answer, right? Because once we decide that okay, we have chosen this slot and whatever, then we will put B and C there in a particular ordering, B first and C next, and then after that whatever the remaining slots are there, that will be filled by D and E respectively in that order. Okay, so the problem boils down simply to in how many ways we can choose two slots out of these four slots, and that particular number is 4 choose 2, and that is our answer, which is 4 into 3 divided by 2 factorial, which is 6. Okay, so the number of different topological orderings of the vertices of the graph for this directed graph is 6, and that is our answer.